So good morning, everyone. My name is Tamika Tannis. I'm a software engineer at Lyft, and we're working on an open source data discovery tool called Amundsen. More on why we chose that name later. So this product leverages Neo4j, and we're here today to share how we've been using Neo4j at Lyft to achieve the goals of our product Amundsen, helping us with data discovery at Lyft. If you're one of those folks that likes to take pictures of slides during talks, you don't have to do that. You'll be able to get all of these slides if you go to go.lyft.com/data discovery slides. Once again, go.lyft.com/data discovery slides. Either right now or after the talk, you can just go download those and follow along. All right, so on the agenda for today, I'm going to start off by first giving an overview of the data ecosystem at Lyft. You're going to need that information to then further understand the challenges that we had with data discovery before this tool was built. Then I'll transition into talking about how data discovery at Lyft currently works now that we have that tool running in production for over a year now. Then I'll transition to talking a little bit about Amundsen's architecture, and then wrap up with a discussion of what we've done maybe around the past 6 months and what we plan to do in the future. So now let's talk about the data ecosystem at Lyft. The data ecosystem at Lyft can be explained at a very high level by this diagram that you see here, and I'll be walking through it starting from your left-hand side. As you can imagine, a lot of the data that we have at Lyft is coming from our mobile app. We are collecting data about every single thing that is happening in a ride from start to finish. There's also the services that are supporting the mobile app that is also firing events and generating data. And then we also have other in-house services that are just supporting all other business needs at Lyft that aren't directly supporting the mobile application. So that is a lot of data. The events are fired into streaming frameworks such as Apache Kafka and Amazon Kinesis. From that streaming framework, we use a tool like Apache Flink to ingest that data into Amazon S3. Amazon S3 is our first layer of persistent storage where that data lives until it's otherwise deleted. The data that is stored in Amazon S3 is further transformed into other data stores. We originally started with Redshift, and then we slowly introduced new data stores with different strengths to better serve specific purposes. For example, we use Hive for long-running queries, we use Presto for quick analysis and as-needed queries, and Druid is very good for faster interactive queries. We also have a variety of applications that are trying to access all of this data. Currently at Lyft, we're using some very common BI tools like Looker, Mode, Tableau. Superset is also an open source data exploration software. And then we have a myriad of custom applications that we've built in-house, once again, to serve Lyft's other business needs. And the takeaway from this slide is pretty much that we have lots of data, somewhere around the order of 10 petabytes, lots of different places it can be, thousands of tables, a variety of different data stores, and a variety of tools and people that are trying to access this data on a regular basis. Now let's go even deeper into the challenges with data discovery. The challenges with data discovery it actually surpasses the fact that there's lots of data and lots of places that it can be. Before we go into that, let's back up and talk about why effective data discovery is so important in the first place. This is because data is at the heart of every decision that we make at Lyft. It's the only way to make informed, objective, data-driven decisions. It also applies to many roles. As you can imagine, there's analysts and data scientists, but even beyond that, product managers, general managers, they're the folks that are responsible for, let's say, our market health in a particular region, even engineers like myself. We need data to verify that the choices that we're making results in the desired impact. And the overall data-driven process, it can be broken up into about 4 steps. First, you search and find that data, then you have to understand that data. From there, you're going to perform some sort of analysis or create a visualization, and then finally, you either share your insights or make a decision. Now, let's highlight some further pain points of data discovery without the proper tools by walking through a hypothetical example of what might have happened at Lyft before Amundsen was built. So let's say you're a new analyst in the fraud department. By new analyst, you could be, this could be your first job out of college, or you could be an experienced analyst, but you're just new to Lyft. Or you could have been working at Lyft for a while, or you just switched to a new team that's having to use new data sets. And so the goal of your team in, I guess, an earlier version of Lyft, when we first released our insurance plan, your team might be thinking, all right, what new data-driven policies can we enact to reduce driver insurance fraud? Someone in the room comes up with the idea, and then they say, well, I wonder if it's the case that we suffer from drivers who are signing up to drive with Lyft just to use the Lyft insurance to cover pre-existing damage on their vehicles. So we don't know if this is the case or not. Before we create some new policy, let's actually look at the data. Let's take a deeper look into insurance claims from drivers who have given less than X number of rides, where X can be just some arbitrary number that has been decided that perhaps drivers who have given less than this number of rides, the chances that they actually got into an accident are pretty low. So let's actually just take a deeper look into that particular case. So as the analyst, you say, great. Next, let me start off by just getting all the drivers who have given less than X number of rides. And so your next question is, but where do I look? Without the proper tools, your process might look something like this. First, you might ask a friend or a manager or a coworker. Say they don't know, they've never looked at that data before. Next, you might ask a wider audience. At Lyft, we use Slack to communicate with each other. Different teams have different Slack channels. So you might end up spending some time hopping around different Slack channels, asking some questions, doing a bit of back and forth and not really getting your answer. Maybe from there, you might just back up and say, fine, let me just look at the code. Let me just look at the GitHub repos. Let me look at the code that's generating these tables and see what I can find. And then perhaps you end up finding two tables called driver rides and maybe rides driver total. From the name of these tables, you're like, okay, this might have what I'm looking for. But then now when you get to the step of understanding that data, there are even further pain points. Right now, you just have a table name that sounds like it's what you need, but you don't know the difference between these two tables. You don't know the differences between the fields. These tables, they have similar names. They have similar field names. What's the difference between driver rides completed and rides driver total, lifetime completed? Who knows? Right? What period of time does the data cover? This is all information that you don't have. And so you dig even deeper by just running a SQL query on these tables to get the first 100 rows of data, to actually just look at that data and say, all right, it's already been several hours. I found this table. I still don't know if it's what I want to use. I'm going to run an expensive SQL query to get the data, all of the data in this table, first 100 rows, and just manually look through these columns to see if it has the information that I want. And the unfortunate part here is that we realized at Lyft that data scientists were spending up to 1/3 of their time on data discovery, on just the search and find part and understanding the data. It was very difficult for them to understand what exists, to understand whether or not it was what they were actually looking for, to trust that it was the source of truth for that information. And that's really unfortunate because at the end of the day, this decreases productivity, right? And it's actually a huge drain on our resources. The strengths of our data scientists and our analysts are their analysis skills. That's what they're paid to do. That's what we need them to do. And if they're spending 30% of their time just finding the information that they need to do their job, that's an incredibly frustrating experience and a drain on resources for the company. So now as engineers and product managers, when we're thinking about the audience for our tool, we're going to build a tool to solve this problem, increase productivity. All right, who should we focus on? In those user personas that I showed a couple slides back, we first chose to focus on analysis and data scientists as our first audience for this tool. When building a product, usually you start with a small audience and then grow it to suit the needs of a larger audience. We chose these two personas because these were the personas that were most frequently using data. They were most frequently doing a deep analysis on this data. They were the folks that were most frequently constantly exposed to new data sets and needed to ramp up on their understanding of those data sets really quickly. And finally, they're the folks that spend the most of their time creating great insights and developing different models. Beyond these two personas of analysis and data scientists, there are also these second level of personas to consider. We have our new user, who is someone who recently joined Lyft, or we have the power user, who's someone who's been at Lyft for a long time. The new user in that hypothetical example that I put forward before, they're going to need to ramp up on a lot of things fast. They just joined this company or they just joined this team and they want to start having impact really fast. But the pain points that they're going to have is that they don't know where to start. They're going to spend a lot of time asking questions, just trying to find what they need. And then in the worst case scenario, they could potentially make some costly mistakes by misunderstanding some of those data sets that they're using. Now, the power user, they're someone, they know the data environment well, they know where to find the data, they know what it means, they know how to use it. But the pain points for them is that that power user is going to be spending a fair amount of time helping out and sharing their knowledge with the new users. And that itself is not a negative thing for an experienced person to be helping a newer person. But the point here, it's around productivity, right? There's no need for another person to be spending so much of their time doing something that a soft piece of software can help them to do. And then also for the power user, they can easily transition right back into that new user persona if they ever decide to switch teams at Lyft, right? The last thing that we considered are the three complementary ways to do data discovery. First and foremost was search-based. This is the case where someone just wants to search for a particular term and then find all of the data resources that are matching that term. The second is lineage-based. If you can remember that slide that I showed showing Lyft's data ecosystem, where there's all of those events that are getting piped into different places and then end up in different tables, if there's some incident and there's actually a problem in our system with one of those events, lineage-based discovery is going to be able to help you figure out, okay, something's wrong somewhere earlier on in the pipeline, which data sets down the line are going to be affected by that? And that's really important because folks need to know that the data sets that they find are trustworthy and not affected or contaminated by any inaccurate data or missing data. Lastly, there's network-based discovery, which is where you might just want to understand what data resources your manager is using, what resources your coworkers are using, just for the purpose of, you're new to the team and you want to be able to use trusted data resources that everyone else is already using for similar purposes. Now that we've talked about some of the pain points of data discovery and why it's important, we'll talk about our solution, Amundsen. The product, it's named after Roald Amundsen. The story here is that Roald Amundsen was led the first expedition to the South Pole and was the first person to explore both North and South Poles. When we were knocking around a name for this product, someone made the connection between Amundsen and data discovery throughout the name, and it kind of just stuck. Now, what I'm going to be going into is an overview of what data discovery at Lyft currently looks like right now that we've built Amundsen. As a disclaimer, the data that you're going to see in these screenshots, it's all representative data, it's fake data. This is not real Lyft metadata. And then this is also an earlier version of Amundsen around 6 months ago. Towards the end of this talk, I'm going to show you what we're currently working on, which includes a new UI and those sorts of things. All right, so our landing page for Amundsen, it's optimized for search. As I just mentioned, the most common form of data discovery is search-based, so we optimized our landing page. It just has a search bar and also some helpful help text on the bottom just to guide our users through some advanced search syntax if they want to use that. We also wanted the landing page to be able to help users who don't really know what to search for when they get here. So we created this concept of popular tables. And we actually display the top used data resources in our organization. So if someone comes to Amundsen and they're not sure what to search for, they could perhaps start with some of the more popular data resources and continue their discovery from there. When a user is presented with search results, those search results are ranked. They're ranked based on relevance and popularity, and I'm going to define exactly what I mean by each of those. For relevance, that's pretty much when you search a search term, you actually want to receive results that are related to what you search for. So if you search for apple, getting a result of an actual apple is high relevance, but getting an example of an orange is low relevance. Now, in terms of popularity, what this means is when you search for something, we want to be showing the results that people are more often looking for, right? And so when folks search for Apple on Google, more often than not, they're actually searching for Apple products as opposed to Apple the fruit. So this is an example of what I mean by popularity. Striking the balance between relevance and popularity has been a very interesting challenge. The relevance matching is based on pieces of metadata such as table names, column names, table descriptions, column descriptions, tags on that resource, and we have different weights for different pieces of metadata. Popularity is based on our querying activity, and there's two types of querying activity. There is automated querying and ad hoc querying. Automated querying, that is when a data resource is accessed as part of some automated job that's running on a regular basis and accessing that data. Ad hoc querying is when an actual user, an actual person decides to go to this data set and run a query. And we weight ad hoc querying that's done by actual people higher than the automated queries that are expected to run at various intervals. When a user finds a search result, they're able to click on it and then view what we call our resource metadata page, or in this case, our table metadata page. Some of the metadata that we show on here, you will see the name of the table, the high and low watermark, which is the first date for which this data is available and the last date for which it's available, the table description. We have the columns, column names, descriptions, the column types. Over on the right-hand side, we have a panel that further shows more information. It shows who owns this table, who frequently uses this table. As I mentioned, our data is transformed from a variety of different sources and put into different places. So we have some links to where this data is coming from, which DAG and Airflow. Airflow is our ETL tool that we use to extract, transform, and load data. Which Airflow DAG generated this table? Where's the GitHub source code? You'll see some tags on the bottom that users can enter, and then those tags become searchable the next time a resource is indexed. So if I wanted to tag resources that my team was using with my team's name, data processing experience or something like that, I'd be able to do that and then actually search data processing experience and then get all of those tables for my team. We also have some more interactive features, those buttons that you see there. We have a Explore SQL button, which when you click it will take you to Superset, data exploration tool, where you can actually just start playing around with that table and running different types of queries. We also have a Preview Data button where if you have access to actually view that data in that table, not everyone can view every piece of real data. So if you have access to actually view that data, you'll be able to see a modal that actually has the first 50 rows of that data, so you can actually check out what exists. Now, another thing that's interesting to note on the resource metadata page, it's hard to see on the slides, but in the columns, there's a small, on some of the columns, there's a small drop down where if you click on it, you'll be presented with column statistics. Right? Our users are going to see when these statistics were generated. And the reason why this is important is that having these column statistics can give our users some insight into the health of that data set and the quality of that data set. For example, let's say if this column that you happen to be looking at or this table is something you thought you wanted to use, but let's say if that count null statistic was ridiculously high, let's say 50% of the entries in this column are actually null, then you know that perhaps you don't really want to use it because 50% of that column is empty. The last feature that I want to highlight is that little pink button on the lower right-hand side. What that is a tool for in-app user feedback. When we were first building out this tool, we really wanted to make sure that we were doing the right thing for our users. Once again, our goal here was to increase productivity. So we wanted to decrease the friction, as much friction as possible when it came to getting feedback from them. So that's why we decided to put this feedback tool in the application itself. Users can fill out a variety of forms to just give us their general feedback on it. They can also file bugs. So if they're actively using the tool and something doesn't look right, something's not working right, they can immediately click that and file a bug report, and then they can also file feature requests. Now that I've talked about what Amundsen is, shown you what it looks like and how it's used, I want to talk a little bit about its architecture and how it was built. So Amundsen follows a microservice architecture. What that means is that there is no one host that is running all of this code. The code that supports this entire application exists on 3 separate services running on separate hosts. The services are separated by domains. We have our front-end service, which is responsible for that UI application that I previously showed. We have our metadata service that's backed by Neo4j, our search service that's backed by Elasticsearch, and then we also have a Databuilder layer that is responsible for ingesting the layer, all of the information from our metadata sources up into Neo4j or Elasticsearch. Now, let me start by drilling down into each of these services one by one. And we're going to start off with our metadata service. As I mentioned before, our metadata service is backed by Neo4j, and it is the front end service will make a request to the metadata service to get all of this information that we're showing on our resource metadata pages. And so a lot of web applications are not necessarily backed by graph databases. Historically, it's not something that folks do. So someone might ask us, why choose a graph database? If you remember, once again, that diagram of the Lyft data ecosystem, that can pretty much be modeled as a graph. We have this concept of application A firing an event B. That event B gets ingested into streaming framework C. From then, it's written to Hive table D. We have Airflow that's transforming that data, reading and writing, so on and so forth. And so the ecosystem that we are trying to express, that we're trying to model, can be expressed as a graph. And we found that to be very powerful, especially for capturing all of these relationships, because our alternative to doing this in relational databases would be to use a whole bunch of joins. That's not very performant. And then other options like NoSQL databases are just not really set up to mimic these kinds of relationships easily. Let's take a note of some of the features from that table metadata page. I won't walk through this entire diagram, but you'll see here that we have this concept of a table node, and then tables have column nodes. Both tables and columns have descriptions, so there's a description node, and then relationships between tables and columns, and things like that. This is very beneficial when it comes to iterating quickly on new features, because when we have a new use case and a new piece of metadata to represent, we just have to create a new node and create that relationship. For example, the tags feature was not part of our alpha release in production at Lyft. And so when we were creating that tags feature, in terms of what we had to do in Neo4j, it was as simple as just creating the concept of a tag node and then creating APIs to either create the relationships between tables and tag nodes or delete that relationship. Another thing that's worth noting about the metadata service is that it's actually a thin proxy layer with the graph database. They're not tightly coupled. The reason for this is that we were aiming to be an open source product, and something that's really important for open source is that different companies, they're going to have different infrastructures, and they're going to want to perhaps like pull out different pieces of the system and replace it with something else that they're using. Specifically, ING, they're a bank in Europe. They were one of the first companies that was interested in using Amundsen in production, and they already had all of their metadata sort of set up great in Apache Atlas, and they wanted to be able to use Amundsen, but also use Apache Atlas. And so for Amundsen's metadata service, Neo4j is the current default option for the back end of that, but it can also be replaced with Apache Atlas or anything else that can serve the same purpose. Another interesting characteristic of our metadata service is that Neo4j became, I guess, our source of truth for our editable metadata. Those table descriptions and column descriptions that you saw in the web UI, those are editable. The reason for that is that not all of our resources even have those descriptions in the first place. So we wanted users, especially the owners of those resources, to be able to go into the web tool and actually input those descriptions. Or if a description was outdated or incorrect, we wanted someone to be able to correct that. And so initially, we were getting these descriptions from Hive Metastore. We started off by ingesting Hive tables first into Amundsen. And so the information in Neo4j is re-indexed, every 24 hours, if not every 12 hours, because we have to make sure that that metadata is up to date. And so the first problem we had was when someone had edited a description in the web UI, that description gets updated in Neo4j. Because the information in Neo4j was going to get re-ingested, we had to update the description in Hive Metastore as well, such that when the data was re-ingested, that updated description would still persist. However, we forgot to account for something. We forgot to account for the fact that sometimes even the tables in Hive Metastore get rebuilt from the source code that's in GitHub. And so what would happen at that point is that the original descriptions that were in the GitHub source code would get overwritten to Hive Metastore and then overwrite all of those newly updated and refreshed descriptions that were in Neo4j. So we thought, well, maybe we can do this. Let's update both Hive Metastore and GitHub. Could we do that? The answer was no. The reason is that making a change to source code in GitHub cannot be automated. Those code changes need an approval from an actual human being. And so once we realized we weren't able to automate this, we decided that there was no way for us to reliably propagate the editable metadata back to these other resources. And so we eventually decided that as far as these editable pieces of metadata goes, Neo4j would be the source of truth. We pretty much hit a roadblock and then decided that we didn't want to go down that road anymore. Now on to our Databuilder service. This is responsible for getting all of the metadata from our metadata sources and ingesting that into Neo4j and Elasticsearch. Now, which metadata sources exactly? A lot of them. From that diagram before, we have a lot of different tables. We use Redshift, Hive, Postgres, Druid, and then the bigger vision for Amundsen goes beyond just indexing tables. It's just about indexing data resources. Those BI tools that I mentioned before, like Mode, Tableau, and Superset, our analysts are building dashboards in those tools as well, and we want to be able to index those dashboards. And so the general problem here, the challenge is that there's no standardization whatsoever. There's no single data model that is going to sufficiently fit all of these data resources. There's going to be different ways in which you're going to be extracting this data. The way that you would get the data from a Hive table in Hive Metastore is vastly different from the way that you would get the metadata from a dashboard in Tableau. And so this is what Databuilder helps to address. It is a data ingestion framework that's similar to Apache Goblin, if anyone's familiar with that software, and it functions as an ETL engine. It is extracting, transforming, and loading that data somewhere else. In this case, another part that's separate from the actual ETL is the publisher. The publisher leverages a transaction to make sure that the data ingestion is atomic. What that means is that there is never going to be partially updated data in Neo4j. All of that ETL is going to be done first, and then once the new metadata is collected, it's just all sort of ingested at once or published via the publisher. Something also interesting to note about Databuilder is that it's modular. These extractors, transformers, and loaders, they can be mixed and matched or reused. Perhaps there's a case that someone writes an extractor that can be used for two similar data sources, especially as an open source tool. Perhaps we write a transformer for something, and for some other reason, some company decides that it's not sufficient, they want to make some changes. They can plug in their own transformer, and so on and so forth. This is an example of a more solid example of our Databuilder in action. We have some metadata in Hive tables. We have a Hive table metadata extractor that uses a SQL Alchemy extractor. For this particular case, we don't need a transformer. That information is loaded into a CSV and then published into Neo4j. The final question about Databuilder is you may be wondering how all of this is orchestrated. It's done with Airflow. As I mentioned before, is what Lyft uses for ETL. This Databuilder can be pretty much represented as a Databuilder job in Airflow, and that job consists of a variety of other jobs. In that diagram, you'll see that we have a job for collecting those table statistics that I showed you earlier, and we have a job for collecting the table usage and things like that. And then we also have a separate job for publishing to Neo4j and publishing to Elasticsearch. Now, Elasticsearch, as I mentioned, that's what sits behind our search service. Similar data is loaded into both Neo4j and Elasticsearch. The difference is that data that won't be searchable isn't ingested into Elasticsearch, and it's only in Neo4j. An example of this would be those column stats that I mentioned. The column statistics are shown as part of the metadata, but the column statistics aren't a searchable feature. So that's an example of something that goes into the Elasticsearch, but not Neo4j. Similarly to the metadata service, the search service is a thin proxy layer on top of Elasticsearch. Our folks ING are also using Apache Atlas for the search feature. So we at Lyft, we're using Neo4j and Elasticsearch. ING is just using Apache Atlas with our 3 services. Our search service supports a couple different patterns. We have the normal regular search where you just type in a word and get the matches based on that. We have category search, which is where folks can search in a particular category. So if they wanted to search only in Redshift tables, they can search, database Redshift and then their search term. We also have a wildcard search. What that means is that oftentimes there are a variety of different prefixes where the exact search won't actually give you the term that you want. An example here, especially at Lyft, are the words ride, rider, rides, plural, and riders with an S. Sometimes you don't really know if that table is called something ride, something rider, something rides. And so the wildcard search just helps folks find things where they know that table or that column might use a particular prefix, but they're unsure of what the suffix might be due to slightly inconsistent naming patterns. What I find most interesting about our search service is actually the biggest problem that we're currently struggling with, which is how to make search more relevant. What we've done, we've experimented with different weights. For example, an exact table match in terms of the name really boosts that search result. An example that I showed in the screenshot before, if someone searches for passenger, and there happens to be a table that's just called passenger, that result should be one of the top results, if not the top search result. We've also been collecting a variety of metrics about user behavior, search behavior in our tool. The types of things that we're looking for is to capture whether or not someone does a search. Did they then click on a search result, or did they not find what they need and did they just execute another search? Did they ever make it to the metadata page? Did they ever preview the data? Did they just leave the application altogether? When they click on a search result, was it one of the top search results, or was it all the way on the 3rd page of results, which is not a great experience and not what we're aiming for. Another thing that we did was introduce more advanced search features. As I just mentioned, we have wildcard search, category search. Something that we're currently working on are more common advanced search features like filtering and auto-suggest. Lastly, I'll quickly cover our front-end service. That is the service that hosts the web application that I previously demoed some screenshots for. This is the obligatory slide where I just list up all of the tools that we're using in case anyone is interested in contributing to Amundsen as an open source tool. We use React and Redux for developing the web application. We use Webpack and Babel for actually building the source, and we use Jest and Enzyme for testing. All of this is written with TypeScript. For those unfamiliar, TypeScript is pretty much a typed version of JavaScript. JavaScript is, a really fun and funky language where you can set a variable to an array or a list and then treat it like a string somewhere else. But then if you do that, perhaps your application breaks. And with TypeScript, these human errors with mismatching types, those are caught on the build phase as opposed to when that code is already deployed into production. So TypeScript was a choice that we made when this tool was getting built for our front-end application, especially knowing that we were going to go open source. And if we ever got to the point where a lot of folks were, trying to submit code changes, we wanted to make sure that we were using TypeScript in order to make our code, especially on our front-end application, more robust. Because when the front-end application has issues, that's very bad for user experience. An example would be, perhaps if there's something wrong with the metadata service, the experience could be that a feature might not be working. But if something goes wrong with the front-end service, it's gone. No one can use the tool, right? And so we wanted to use TypeScript to make sure that that was robust. Another interesting note is that this front-end service is sitting on top of Flask, which is a Python web framework. Our search service and our metadata service is written in Python. Most of the front-end service is written in TypeScript, but there is a Flask layer that the application is actually sending the requests to, and then the requests that are in that Flask layer, that's actually what's talking to our metadata service and our search service. So underneath the hood, we have across all of these three services, Python talking to Python. It's led to some efficient ways for us to create some standardization across all three services. For example, our logging framework, the framework that we're using to collect all of this information that's happening in the web application, our logging framework was written in Python, and it can be used across all three services because we made the choice to use Flask as a layer on the front end service. Lastly, let's talk about Amundsen's impact, what we've done since circa March 2019 when we first started giving this talk, and what's next. So Amundsen has been really successful at Lyft. It's currently used by not just the initial personas that we were aiming for, which were analysts and data scientists. We currently have engineers, PMs, even customer service folks are using Amundsen to find what they need. We have 90% penetration among data scientists, which was one of our target personas. What this means is that 90% of data scientists are using Amundsen to do their jobs on a weekly basis. And then we also found that this tool has increased productivity for our entire data science org by around 30%. As I've mentioned before, Amundsen is open source. You can find this project and this code at github.com/lyft/Amundsen. We currently have 10 plus companies that have contributed some code or some changes. We have a Slack channel. You can find the link to that Slack channel in our GitHub repo. We have a Slack channel with over 100 people. We've been presenting at various conferences in San Francisco and now Santa Monica. Our folks over in Europe have also presented at some conferences in Europe as well. And we've done a couple blog posts. Here's just a general community overview of some of the people that are currently interested in Amundsen or actually using Amundsen in their companies right now. I'm going to wrap up with an overview of our roadmap. So our first phase was just ingesting data sets for people to be able to search, which we've already completed. Our second phase in progress, we wanted to ingest more types of data resources, such as dashboards and people. Well, why people? If you remember that network-based data discovery that I mentioned before, where you're going to want to know what resources are other people in my job role using, or my manager, and so on and so forth, we've actually completed that within the past 6 months. Right now at Lyft, if you search my name in Amundsen Tannis, you'll actually get me as a search result, Tamika Tannis. When you click on my profile, you'll be able to see more information about what team I'm on, my manager, my contact information, and then more importantly, you'll be able to see the data resources that I've bookmarked. We have those Amundsen tables there. Those are my bookmark tables because it contains all our metrics about how useful this tool is. So that's a table that I happen to be looking at all the time in my own tool. And also my frequently used tables, and then any tables that I might own. Another thing that we're working on or in scoping is ingesting things like streams, workflows, doing deeper integration with other business analyst tools. This concept of just ingesting tables and showing table metadata is just scratching the surface of what we want Amundsen to be. Here's an example or a mock of how we want to change our search experience. This is what we're going for in the future, where when you search in Amundsen, you'll be able to see, have a helpful auto-suggest feature that'll help you find what you want more quickly. You can see that in these mocks, we have a variety of different data resources, data sets, pipelines, dashboards, people as well. We're also currently working on a major UI redesign that is going to be surfacing more metadata. You might notice some similar metadata from the previous screenshot. You see the table name, the owners, the columns, column descriptions, and things like that. But on the top left-hand side, there's a little flag or a little alert there. One piece of metadata or pieces of metadata that we want to be able to start showing in Amundsen is related to quality, right? So in that example of something went wrong with one of the events that generates the data that ends up in this table. If there's something wrong with that event, we want to be able to capture that and show that in Amundsen as well. We want to be able to show different quality flags or different specific badges on the columns. In the previous talk, we're talking about data privacy and things like that. One of these flags would be personal information for being compliant with CCPA to actually understand where personal information exists in all of our tables. And that wraps up my talk. My GitHub is at @ttannis, and you can find me on LinkedIn at Tamika-Tannis. Once again, the project code is available at github.com/Lyft/Amundsen. And then we also have our first blog post up at go.lyft.com/data discovery blog written by our product manager. We have another engineering focused blog that's going to cover some of those architectural decisions coming out soon. And I'll be happy to answer any questions that you have, or you can come find me at the next break.